Hello everyone, I'm Cole. Yes, this is from May channel. Uh, I'm very, how can I say, very nervous to make the first video clip for the first time, and then so that's what. And then today's topic is very arbitrary, but the is too arbitrary is not good, and then that's what I want to give you. So any kind of topics from you is about. So yes, this about the material science engineering, and then that is my majors. And also I studied the research this topic more than 20 years. That's what I'm. It's also very useful. And also I just person who studied this topic before. I think it's very useful guidance for you to give you some good understanding toward this kind of majors. You are just kind of high school student, and then so you are very hesitant what kind of the major I'm going to choose. Yeah, in a university, more science engineering or medical science or more law school. Yeah, for your better understandings, and at least I want to talk about material science and engineering. Here most of the departments from the name of department we just realize, and then especially in science engineering, and then this department is more close to the science and more close to the engineer. And then simply you can ask some kind of question, and then what is science and what is engineering? This is very basic question, also very important. Okay. In the meantime, I simply let you know this is my first time. Also, some of you may just log in the system for the first time. So there must be the system and there's some kind of blank, and then you can upload any kind of information, queries, some kind of question you may have into the system, and then I'm going to read and I answer to the kind of question, and then any kind of word is very good. Yeah, there's someone. Yeah, yeah. Hello. Yeah, we have several members, and then so unlike my expectation, and then I'm very happy to see this kind of the members, and then once anyone is comes into the system, and then oh yes, maybe yes, yeah. Hello, and then I cannot see the person's name very well. Anyway, hello, yeah, hello everyone. So we just back to the original topic. What is the science and what is the engineering? For your better understanding, what about the chemistry, mathematics, and then physics? The chemistry is more about it's pure, right? It's not applied one. What about mathematics, statistics, and then chemistry, life science, life research work? This is all about pure, pure the science. That's why we can call this science. Engineering is more about the how can we make some kind of profit, and it's most can be used more practical tools, and then for instance mechanical engineering, it can be used, yes, automobile, aerospace, right, machine part, machineries. It's all kind of important components, and then the mechanical engineering can take part responsibility for these kind of things. And then what about chemical engineering? Chemistry and then chemical engineering sometimes very confused, but chemistry is about more reference scale, and then the fundamental aspect. The chemical engineering, something happen in the factory. Yes, how can we make some kind of formula to make some kind of profit, to shape some kind of plastic material, to shape some kind of composite material? This is all about chemical engineering. What about material science engineering? Yeah, this also the backbone. How we just create new material, the rather than creating new materials, and then it's about the polishing and then provide some kind of so understanding toward the advanced material concept. This is material science engineering. But unlike other departments, chemical engineering, mechanical engineering, electrical engineering, but material science and engineering. Why material science and engineering in both together? 자, for this one and then I will show you some kind of writings and then for instance, 자, actually the system is pretty unstable, but hopefully and then you can understand. I need your patience more and then. So let me write it down some kind of specific scope and then science and engineering. And then we just say, what's your dream? And I remember it's more than decade years ago. I remember and then the teacher in elementary school. And then please write it down your dream. And the moment South Korea and then more than 80% students, especially men, the kids and then they will choose this kind of dream. I want to be a scientist. All scientists, including me. Why scientists? The time and then there are many cartoons in the broadcasting, KBS, MBC, and then it's all about some how can I make the robots. For instance, 메칸더브이 and Mazinga Z. There are something like this and then atoms and from the Japan. That's why we really curious about the. There are some scientists who make this kind of system, robot, a very fancy one. That's what I want to be. And also there are some kind of social necessity and then. So our country in South Korea, unlike maybe I don't know, you are from the Australia, you are from the United States, and then your country is very abundant in natural resources. But the South Korea, we have no. Even the manpower, the moment, and then resources from our ground, everything is very rare. We are the very short of these kind of things. But the matter and then, so we only just think about and then how can we just educate the next generation? So because of this one, we can grow up. Anyway, at that time, that's what and then the government intentionally make the science and engineering grow up very rapidly. This is our government plan and then. Why? By changing some kind of social infrastructures and then we can go to more developed country from the developing country and then. So we did it. That's what most of kids dream is to be a scientist and then. Also, so do I. I just remember that. So that's why scientists, even I don't know what is the meaning of a science. Scientists coming from the science. Scientists coming from the science. But there's some of a student and then my friend, he just talking about I want to be an engineer. Remember that. The moment we don't know English very well. And how do you know engineer? But he may know these things and then yeah, I just write it down. 과학자 in Korean language, but he just talk about engineers. Wow, maybe engineer seems to be better. But in any case, that is not important. And then the science, once again, I just talk about is about the pure categories. Engineering is more about the making a profit for the practical application. Then, science, and then we can see the physics. And then chemistry. Yes, I remember that. Someone he intentionally looked down the quality or research work of chemistry, and he simply say, "Chemist, try." Actually, this is not good meaning, and then anyway, there are something in them. But nevertheless, these chemistry also have some kind of good meaning, and then try. The science cannot be developed without any kind of trial error by the scientists. So what about the mathematics? Yes, simply I just say math, and then something the other, something statics or some other things, and then this also just kind of the category you categorize as a science. Engineer, and then chemical engineering, mechanical engineering, electrical engineering. There are many things. One of them is the material. And material always need S. Please remember that. Materials. Materials scope should be. I just write down the materials in the middle of science engineering. Material, this major can cover the science part, the tailored new kind of concept of advanced material, and also can be used as some kind of real component in automobile and aerospace, any other some kind of vehicle, and very important as a mechanical component. That's why material science engineering, this kind of major is so unique, covering whole science and engineering. There's one more thing, that is computer science and engineering. But now the computer, this kind of concept and history is now well developed. That's why we can say, maybe computer just engineering, but still we need to upgrade and then need more understanding how to make some kind of circuit system for the calculation. And then now still developed. That's why someone still say computer science and engineering. Engineering application, then we really use the computer every day, right? This is a practical goods. That's why then it also cover engineering. What about the AI? Yeah, AI is associated with just part of mechanical and electrical engineering and then computer engineering, computer science. It's all collection and science engineering. That's why and then from now on and then there is a new major, new topics. It cannot be categorized into one in one. So sometimes it can be the science, it can be the engineer. Even do you know this kind of concept? Multidisciplinary. Previous case in the material science engineering divided into 3 different pieces: polymer, ceramic, or more composite material. But nowadays, and there this kind of concept is almost broken. And then across the material concept, across the properties, for the special necessity and also characterization is now shared. That's why we cannot say metal only for the material science. No, sometimes metal can be used for chemical engineering. There's no border and scope anymore. That's why under the name of the interdisciplinary or multidisciplinary, and there's no boundary anymore. So the one of the questions, and then someone really wants to know what is the material science engineering, and then okay, this is very important question. Once again, I just let you know. Okay, you are the material scientist engineers, and then, so that's why. Can you define the clearly and then the concept of material science engineering? I just remember I just joined up. I just applied for the master degree and doctor degree in my university post-tech. And then some of the referees, some professors asked me the question, and then as a fundamental question, it's also very difficult to answer. What is the material science engineering? What do you think about that? This is very open-ended question. And then I can say material science engineering to study more polish the sample. Yes, it's just kind of routine job. And then observe the microstructure. Yes. And then we use several machines, observation. And then we can do some kind of, the moment I'm more about the physical methodology and do mechanical testing. So like this. Yeah, maybe if I just say in there well and then, so my score is very poor. Maybe I cannot pass the test and then. So this is a very representative example, but you must write it down for this kind of question. And then so let me. 자, MSE 테트라헤드론. We can draw this line. And then how many corners? We have 4 corners. 1, 2, 3, 4. The 4 corners. 자, each face have the 3 different corners, right? And then how many the faces in that? Yes, the 4 face. This one is very structurally stable. So that's why once you draw it, and then at least you gain some kind of 50% of score from that kind of questions. Why? You understand these things very clearly, and then I need to write it down, each components at the corner. And then first of all, the most important thing is structure. Why you didn't write down? Some people say, oh, your majors, the major you want to talk about today is material science engineering. That's why you start with the material, not structures. The here and then most of materials, and then for instance metallic material, we just polishing. We clean the surface very well, and then etching the surface, and then eventually in order to observe the microstructures structure. And then unlike our expectation, and then the microstructures appears in them consisting of some kind of grains, and then either it might be some equax shape, or Wiedemann statin, or bimodal structures, and any kind of the combination. So that's why I think the concept of structures is more stable than just material. Material just kind of a pattern and aspect things, and then that's why I just write it down, structure. But this structure, and maybe more than 30 years ago, microstructure, and then micro means 10 to minus 6 meters. Micro level is so tiny, and then the time, and then so our understanding toward the material science is not so high. That's why micro level is sufficient to understand the material behaviors. Now, nano, nano, you can hear this kind of terminology before. So sometimes say, and then microstructure or nanostructure, or some gigastructure, megastructure, macrostructure, microstructure, mesostructure. But any some kind of several concept, I can write it down. Structure. Remember, structure is the concept. Okay, structure. And the next one, we just believe this structure can change. Which one? Material properties. 자, what kind of property you like? I can guess the first of all, physical property. As example, elastic modulus. Maybe if you really interested in this physical property, so-called, and then for instance, in some kind of elastic modulus, and then it just encourage you to visit the main channel, and then find the first video clips, and then that is about bonding behavior. This bonding behavior really close to elastic modulus. That's what, and then I hope that you can enjoy the kind of this clip, and then so I just made one chapters consist of 5 different ideas. Physical, and we can say like that, and the chemical properties, right? The chemical, this also so broad. So corrosion property is a part of chemical, because the corrosion is simply based upon the chemical reaction. So that's why my corrosion property, more specifically, and then corrosion density, corrosion potential, this property, or sometimes a more practical one than salt spray, and these things in the mechanical properties. Except the as a fundamental one and then physical and then chemical properties, and then I want to give more highlight to mechanical properties. These mechanical properties and then just kind of reliabilities of material itself. Most of material exposed to some kind of severe condition under specific loading condition. Yes, all kind of material receive some kind of loading from outside, and then that's true. And then what about that? We just make aircraft, the surface of aircraft or some kind of specific but important parts in an aircraft using just kind of normal material that may have some kind of defect and a grain size is very high, and then the property is not suitable for the kind of extreme voyage into the airs with high speed, and then it's not suitable. And then there's some kind of matter, some defect can be generated, and then there's some kind of the crack severe, and then the aircraft will be falling down, right? This is about our human safety, and then so that's why mechanical, the achieving the suitable, the range of mechanical properties is necessary for the making this material useful in the real applications. And then what kind of mechanical properties? And then yes, and then let me write down the yield stress, and then elongation, and there are the others, and then so simply, and then strength and ductility. Yeah, someone said, and then what is the hardness and strength? Okay, I will talk about this issue later. Why? It's very confusing, and then hardness and then strength is also different. Like this one, elongation and toughness. Elongation, toughness also actually is the really closely proportional each other, but they're in a specific definition, and actually those concepts totally different. But anyway, as a broad sense of the properties, and we can say strength and ductility are the representative mechanical property, and I also work for this one and by using several processing methods using the intense process training. What about nowadays, and then for the long life, and then biomedical? Yes, biomedical properties. What about energy properties? Energy means, and then energy conversion, energy harvesting, all kind of property will be included. And then what about environments? More photocatalytic activity, catalytic reaction. Those are all kind of property. There are really many things in them. So the linear relationship between the structure and then property. Property is kind of as a result of the structures. Structure determine the properties. In the kind of case, if this is right, structure comes from the property later, and then we need to control structure to enhance properties, right? This is a logical structure. And then so how can we change the structures? By processing. And in South Korea, maybe broadcasting will be over at 2 or 3 a.m. and no one just watch the TV, and then broadcasting, the company just closed the channel. 1 second before, and they just turn on the national anthem together with some kind of several the videos, and then I also remember that 동해물과, and then this kind of songs, and then we can see some kind of rolling process It surely must be the from postcode loading process and some sample, sheet sample. The red one is moving forward, and then it should be in stretched one, and then maybe you may know. Also, you also know still manufacturing process in your country, and then this is very simple one. This is we can call this one a processing. By this method, especially we can call this hot rolling process, and then to control the structure. And then this processing, especially for metals, and then there are two very important, and then the first one, and then forming, deformation, forming. Okay, deformation, and then temperature. Simply temperature. There are two energy source to give us some kind of energy into the material. The first one by the strain. Strain means, and then so here, and then one material, and then there's some kind of shape, and then so we just give a deformation in this way and this way and this way, and we can shape the material arbitrarily if you want, and then as you know, this is a deformation. One of the deformation method is rolling procedure. What is rolling? There are two rotating roll, cylindrical shape, and then it's roll deformation, and the material went underwent the between two different roll and received some kind of amount of deformation. This is a strain imparting method that we can call this, deformation processing. What about that? Sometimes and then energy can be stored inside the structure, and then okay, what about that? You just work very hard, and then before your midterm and then final test, and then you are very stressful. And some part can be rigid, and your shoulder need to be relaxed more. And then maybe some people just go for sleeping. But what about the sauna? They put your body into the hot bath, hot tub, and for a long time, and then you just feel this part can be relaxed, right? It's just kind of heat treatment. What about that? You make the noodle, some ramyuns, and then sometimes at night, and then so maybe I can just eat just rare ramyuns. Yeah, we can eat it, and also I like it, and then together with some kind of soup inside, and then but that the more appropriate form, and then to make you happy, and then so you need some kind of pots and some burners and the furnace fires. Make some kind of noodles, and then you just put your noodle ramyun into the waters whose temperature is really high up in 60 or 70 degrees Celsius. Even actually 100 degrees Celsius because after vaporization. But the average temperature inside the liquid should be in 70, 80. And then this is a kind of heat treatment. By this method, rigid that noodle become more softer, right? Like you experience into the sauna, your rigid shoulder becomes more soft, and then this is a kind of the heat treatments. Yes, there are several heat treatments: annealing, aging, tempering. What's the normalizing, homogenization, and then actually this one is to increase the temperature. Same concept, but each word have their specific meaning. So later, if I have some time, and I can show you and there's some kind of logical and then scientific difference between this kind of concept. It's very, very useful. But now we're just back to here, and then processing, and then we use a strain, some kind of giving a force to the sample, or we just give some more soft energy and then a temperature gradient to the kind of sample. This can be the processing. So once again, I just talking about it, and then processing can change the structure, and then structure after the changing by the processing can alter the final property, this kind of concept. Oh, if that is right, and then here we just attain certain properties, and then but we using some kind of classical approaches and some kind of conventional processing, and then change the microstructure, but the property cannot meet our requirements or some company requirement, and then we need to change it processing. More higher temperature sometimes, okay, higher temperature is more relaxed one, and then so maybe but dislocation grain structure, actually you don't know this kind of concept now, and some of you may know this one, and then so material becomes softer, and then but then we'll try to make our sample harder, and then the temperature should be decreased, and then right, and sometimes what about we can make some sample stronger by giving more strain energy inside imparting to sample. That's what, and then these three different the concept, this one correlated each other, also interdependent, and then only I just take it and structure. Only I just study the structure. No, there is no research works, and then structure. Simple the control of the structures, and then this one is more than 30 and 40 years ago already done. So that's why you just introduce new methodologies, and then physical or chemical or heat treatment or thermomechanical is kind of combination of two different energy into the materials, and then to control the microstructure, and then down to nanometer level or specific bimodal structure or miscible, immiscible or multi-components. Yeah, we can change the structure, even amorphous structure or crystalline, non-crystalline, and then it's very wide, and we can change this kind of structure. What about then, and then the combination of two different material together, metal and ceramic? This one concept is a layer by layer concept, but sometimes what about this? So bonding kind of case, and then covalent bonding, ionic bonding, and metallic bonding. Yes, maybe you can understand this one, and then all of material have some kind of specific bonding between two different atoms, and then we just conjugated two different systems into one. Metallic bonding and ionic bonding or covalent bonding. This can be the new composite material, right? That's why we can change the specific structure never designed before by the scientists, and then so once you just create a new material concept, and then it's good for your paper publication. Then so we can control the structures, and after that we have to measure, assess the properties then by using several methods. But now I just talking about the macro was changed into non-micro, micro into the nano. Material itself is so small and tiny, and how tiny it is. Did you know the submarine? Yes, submarine can be used for the military, right? Beneath the waters, and then that have some kind of bomb, and then there's something razor inside, and then just attack the others, and then. But now I'm talking about the military submarine. Submarine is so tiny submarine. Then how tiny it is, and then is almost smaller than the size of the blood cell. Yes, and then we have to make some kind of small things, and then and into our blood cell, blood lines, and then there's some so much of a cholesterol on the inside, and then that's why sometimes that we need more high pressure in blood. It's not good condition. That's why this submarine has some kind of small knife in front of this one, and then remove some kind of dust in the inside. Yes, in the kind of case, and then what kind of property, what kind of structure, what kind of processing. Yeah, and then we need to think about new things, and then by using the ordinary or traditional methods, and then we cannot characterize. Even we cannot show that some kind of property that is there, and then someone say, "Okay, I understand that. Okay, let's back to the white screen, and then there's still one more elements, and then what is these elements? that are confusing. And then someone say performance. In performance, let me write down. Performance. Performance, the same as property, but the different thing in the performance for the more, how can I say that, the near to the real shape. And then the final products. The property is a small tiny one, not talking about the, okay, not consideration of final shape. And then the original one. So those are the talking about how, what kind of some material behavior. They just define the material behavior, but its performance is more about the final component after process is all over, and the properties is about the pure and more the fundamental one. So that's why I don't like the performance. And then even if someone just still choose the performance. And then what about simulation? Simulation. The now we live in the era of the computer science, and this computer science is connected with artificial intelligence, right? And machine learning. There are many new things. And then we remember this some kind of final battle between the Lee Sedol and the computer AlphaGo at the moment. And then maybe this really first match and also last match, as far as I know. And also Lee Sedol, took the one wins from the computer. And then someone said that, oh, maybe how can we just win the AI? The moment plug out plug out electricity, it's just kind of stupid. And then AI is always there. And then in the case of the computers, and then so that's AI, they conjugate together. So we really live in the simulation world. And then everything can be expected. Okay, for instance, weather forecasting. Every day we can see weather forecasting at the end of news. And then tomorrow the 50%, something, cloudy and windy, sunny. So that's why you have to prepare some more thick clothes, right? So that's why keep your body against some kind of cold weather. We can see these things in them. So how can we expect this one? Yeah, collecting many information we can expect, and then we just give us some kind of forecasting. And then this is a kind of simply based upon the simulation using the so many data. So we really live in the computational simulation. So simulation or theory. Theory is more essential. Why? This theory. How can we? Okay, what is the theory? And then theory, I think theory just can be our experience. 자, you control the microstructure by using processing to achieve certain properties. We have done this job so far. How many years? More than 200, 300 years. Why? Really 300? What about alchemy? Natural alchemy or pure alchemy. And then so they use ordinary method, mixing method, right? Mixing method at high temperature, and they choose the different material in the inside the bath, and then they just fabricate it. Their final products property should be glossy and color. Should be like a golden. Then not talking about some physical, mechanical, chemical. They don't care about that. They only make some kind of golden. I know it's impossible. So they did this one by the trial error many times by the several scientists. And then please remember, even Isaac Newton is a great scientist. And then actually he's alchemist. And then more than 40 or 50% his research work, he really dedicated his life to fabricate gold. What about the gravity, F equal ma? Yeah, this is also differential equation. And then his great achievement, but we can say, and then he is material alchemist. And then So by gaining some experience from the one experiments, and then we realize some kind of connection, we add something, and the property will increase and decrease, and then by the many times of training and then real experiments, we know, and then we just make some theory. Eventually, we just arrive at F force is the same as m mass multiplied by a accelerated velocity, and then right. So write this way, and then more hardness will be inversely proportional. The grain size. This also empirical equation, and then this equation can be the one theory, and then so we can set up some theory. So that's why collection of our wisdom in a specific area, that can be the theory. Theory without any kind of experiments, there's no validation from the experiment side. This one is just nothing. It's not a theory anymore. Should be validated by the experiment. So that's why, what is your result? Simulation or theory? But I prefer theory. But any kind of natural behavior, this kind of three different connection, can we make some kind of theory all the time? Even you know that there are many variables. Even these variables interdependent each other. Even we cannot say, okay, what about it? There are 3 persons and they just work together, and then you got some A plus from your presentation by the professor in a specific class, and then so that's why who contribute more and less. Each person can make some argument like this one, and then so microstructure have so many structural factor inside, and then so simply, and then under the fixed amount of the other elements, or fixing some kind of structural variable except only one, and then we can arrive at the final question, A increase and the property will decrease. But this is very difficult. Very difficult. You know that multi-component, that some material consists of 3 different elements, A, B, C. Okay, I really want to know the load of A constituent, and then or A elements, not B and C. Here the correct case, and then B and C should be same and A amounts should be different. But you know the A plus B plus C should be 100, right? So that's why, okay, A increased. A is now 50 and B, C should be 50, right? And then A just increased, and okay, up to the 70. And then P plus C is not a 50 anymore. P, C amount also decreased. A is increased, B is decreased, and then so that's why this result is coming from A increase in an A or decrease in B and C. Even B and C is very still an argument. We don't know. And then do you think in the microstructure is uniform? It's not uniform anymore. Even the same sample, under the same experience processing, deformation and heat treatment, and its microstructure is different. This is some kind of gradient behavior, and then so it's hard to say it, and then 1 grain. But still we just train, experiment, many trial errors, and then we can gain some kind of linear relationship between A and B. So it's theory. So that's why finding theory is so difficult. Once again, I can talk about that. So I want to give more highlight. Simulation. But there is the concept, and then by combining simulation and theory, one thing, and then understanding. This is my private opinion, and then you don't need to follow me. Maybe still you just claim, and then there should be the performance, there should be simulation, there should be theory, and then you can find it. Even these kind of things, and then you just give us a MS tetrahedron in the Google. And also you can find the first page of Octamotor. There is the most prestigious journal in metallic material. And then there is also provided different category concept, and then so I just respect your opinion. But the point is, and then I just said, and the last component should be the understandings. Then understanding is about the relationship and how processing can change the microstructure and the structure itself. Or this structure we can have the control, and then what kind of property will be expected, and then it's rather increase, decrease, and then this kind of connection to increase the properties, and what kind of processing method suitably chosen. And then the last time, and then we have some kind of small the project with the company Hyundai BNG Steels and in Changwon, and then they have some kind of critical issue, and then they didn't open any kind of details of the processing condition, and then we just analyze the microstructure and then measure some kind of properties, and then in a reverse way, and then the final outcome is not the meeting some requirements by this specific company. That's what, and then we just suggest, and then we don't know, we cannot touch it, we don't know any condition of your process to manufacturing standing still at the moment, and then so we just propose using this reverse algorithm. But for the reverse algorithm, okay, this is a very difficult concept, and okay, I will just explain that. Anyway, we just use some kind of specific one, and then we can achieve some kind of understanding. That's why this understanding will be the first elements that regarded as a very important elements in the material science engineering. Look at the some question. I hope that you understand this one, and then any question, and then so someone may use some is Korean language, and then so I don't know. There's something here, and then today, and also today I just described the fundamental concept in material science engineering, and then I hopefully, and then you gain some kind of better understanding this kind of behaviors, and then there's someone just talking about, can you give me some kind of example, right? So okay, here, and then I will show you some kind of the best example, and then how can we just control the microstructures and the processing behaviors, and then sometimes a direct experience is very useful, make you to appreciate and understanding this kind of material behavior very well. Also, it's just kind of advertisements of the previous chapters, and then we already just talking about some kind of behaviors, and then so the first example is about the bonding characteristics, and then so it's almost done. The next time, and I have to prepare everything, and then the structure. Structure is the first beginning, the first very beginnings, and then starting the material science engineering, and then structure, properties, and then processing. This is a real example, and then structure sometimes and is associated with certain one, and then the bonding characteristics, and then bonding feature. The bonding, there are two different bonding, and then the first one is primary bonding, and then next bonding is secondary bonding. What is the primary bonding? So that's why primary bonding is more important than secondary bonding. Not the kind of concept. The primary means, and then the atom to atom. Okay, we have the one elements right? Sometimes we have some kind of molecules, and then the molecule consists of the elements. That's why and then this kind of connection. So primary is associated directly with some kind of atom inside, and then so the how many the primary bonding? Yeah, the first one is ionic bonding, right? Ionic bonding and covalent bonding. Covalent bonding. The last one is metallic bonding. Metallic bonding. What is the this also the frequent question and asked by the so many professors and teachers, high school, middle school, and university. Even if you are the doctor and the master degree, doctor degree course student, and you surrounded by this kind of question before the fabrication of your material selection, and then ionic bonding, and then maybe high school student can talk about that one metal positive plus non-metal the negative, and then make a bonding. Okay, representative example is Na plus, right? And then Cl minus, it's chloride, and then final components NaCl. It's rock salts. It's salt, and then as you know, halide structure, and then so this metal is non-metal. That's why this kind of bonding should be ionic bonding. Well, from the periodic table, and then two elements far away from each other, and then this possibly makes some ionic bonding between two different elements. But this explanation is very confusing. Why? Can you explain covalent bonding? Covalent bonding, ionic bonding, it seems to be identical. Even many high school students very confusing. That's why they just memorize, and NaCl, this one is ion bonding, covalent bonding, CH4 it should be the covalent bonding. It's not good things, and then so covalent bonding, ionic bonding, please forget this kind of concept. Yeah, maybe high school is still valid, but I can say four lanes electronegativity, and then each element have their own electronegativities suggested by the polling, and then so this difference is so huge enough, and then the bonding should be ionic bonding, and then the gap between the two different value electronegativity is so small, even negligible. It can be covalent bonding. And then what about the carbon material? Carbon material is ionic bonding. Yeah, from this kind of CC. CC is not a non-metal. Okay, there's no metal, and then you simply say that is covalent ionic bonding. No, but from the electronegativity, we just realize it's just kind of covalent bonding, and then understand. Please remember electronegativity. This is a very important factor to describe it, and then ionic bonding and then covalent bonding, and then you still some kind of question, and then 100% ionic bonding or 100% covalent bonding, this kind of material. No, some also material, and then covalent ionic front and then covalent front. So that's why we have to calculate the percentage, and then even NaCl is not 100% ionic bonding. It also have some kind of certain the character is coming from covalent, but this fraction is relatively lower than ionic bonding. That's why we can say ionic bonding. Metallic bonding is metal, and then metallic bonding we always talking about free electron. Free electron is delocalized. delocalized. Free and delocalized is the same word. Where is the electron inside the metal material? Everywhere. Electron is everywhere. That's why we just give electricity from one chopsticks at first end of the chopsticks, and then electricity comes in, and then you can see another electricity. While you can put your chopsticks by mistake into your pots during the boiling for the ramens, and what happened? And then 1 minute, 2 minutes later, and then you try to grab the chop. Oh, it's very hot. You feel some kind of heat, right? It's just kind of move on the phone, and then so heat or electrical transfer is very high due to the existence of electron inside. Or this one is also affects some kind of ductile behaviors, and then this is also very interesting to talk about. So these three is the primary bonding, and secondary bonding, maybe chemist guys and most like it, and then Van der Waals. Van der Waals bonding과 하이드로전 bonding. 자, the Van der Waals bonding, actually most of the molecule have some very neutrals and electricity, and then it's not the plus, it's not a negative, but each molecule here and then some big molecule, and then some locally this part is more about positive dipole to make a neutralize, and the other side should be negative dipole. Same way, this negative dipole and the positive dipole. Actually, there's no bonding between two different, this cluster, but is plus and minus. That's why there must be the bonding between them. So what do you think about is local, electrical neutralities in a local area is broken by the some kind of movement, by the some kind of local the dipole system inside the molecule. Anyway, whatever, and then so that's why then plus and minus exist, and then they just stay together each other, making some bonding between them. This is the Van der Waals. That's why you can expect this kind of bonding so weak, and then once we just increase the temperature, they set apart, and then it's easily. That's why the bonding characteristic is so small. What about the hydrogen bonding, and then representative example should be H2O. Any bonding connected with hydrogen itself, this can be the hydrogen bonding. So best example is H2O. Why you talk about H2O? The recently we just make some kind of miracles about that, and then so H2O, this is very specific material. We live in the Earth's crust, and then this kind of concept, and H2O is very used, it's very common things, and that we don't know these any kind of properties very well. But H2O is very rare in the universe, and then rare, also extraordinary, and then why talk about the waters and extraordinary? What about the volume expansion between the solid and liquid, and then normally, and then solid material some kind of packing arrangements, and the liquid means, and then there's some kind of there's still some kind of connection between them, and but it's move around freely, and as compared to a great extent as compared to the solid material, and then in that kind of case, and then solid, this one is like the military, and then many soldiers in some kind of squares, and then many things inside. Liquid, and then it's out of control. So that's why the final volume of liquid should be higher than solid, right? What happens? I just remembered, I really drink very cool Coke and Coca-Cola. And what should I do? I just put a bottle of the Coca-Cola into the fridge. right? 1 hour, 2 hour, but sometimes I just forgot, and then later I just open, I just surprised, and then the bottle of Coca-Cola is broken. And then why is it broken and no one touched this one? And then yes, these things happen. Severe temperature drop, even cross the line and freezing points, and then so rather volume when these liquid is change into transit into this solid one, and then volume really expanded, and then that's what in the glass this container will be broken and then they crash away. And then my mother just come to me and then what's the matter, and then there's something, and then before that and I had to clean it up. So this kind of experiment, and then how can what kind of things we know, and then so H2O water show the different tendency. It's the contradict to our general beliefs, and then why these things happen? Yes, H2O. H2O is very strong molecule structure, and then let me draw, and then is the structure. 자, oxygens. How many the valence electron? 1, 2, 3, 4, 5, 6. Right? And then 1 electron from hydrogen, another electron from hydrogen. Yeah, and then now very stable. 자, oxygen surrounded by how many electron? 1, 2, 3, 4, 5, 6, 7, 8. 8 electron outside, and that's why O is very satisfied and obeying octal load. This one. So I just change this one into line oxygen H, right? H should be just positive one. What about this electron? Electron should be minus. This is the minus part, right? So it seems to be this part is more about the positive, this part negative. Like a Bandera bars, and then we can expect to the same thing, right? But here the kind of case, and then maybe there are some hexagonal structure once it change from the liquid to solid. I don't talk too much about it any. So liquid kind of case, and the structure is moving around, floating around freely. That's why it shows some kind of compact behavior. But it becomes the solidified, it has some kind of specific structure in them. So there is a big hole inside H2O structure. That's why volume will be expanded to some great extent. So that's why it's very different from any other quiz we just encounter. But I know, but you know that unusual become the usual, and then so water is near to us. That's what, and we just think about. But once again, even this information is very useful for the just ordinary person and not science engineering, and then so that's why you must be careful in the don't put your some Coca-Cola the bottle anything in glass container and outside, and then during the winter season, and then so this is the bonding features, the primary, secondary. And then I want to give you some example. This bonding, right? This bonding. So there's some bonding, prime bonding, and bonding structure is very strong and secondary small, right? And then this, and then we just think about the motor becomes stronger. That is the suitable direction, and then for some kind of case, in a soft and then fragile motor can be used, but in most of case, and then structurally stable and then durability enhanced. That's why to make the motor stronger in terms of elastic behavior and plastic behavior as well. And then so one of the elastic behavior is some kind of physical properties in elastic modulus, and then so elastic modulus, we need to increase the elastic modulus, and then this means, and then in our previous chapters, the first video clip and chapter 1 bonding, and then simply let you know, and then higher elastic modulus, this means in the melting temperature will boiling temperature, this kind of temperature, transition temperature and phase, and then should be increased, and then right. So these things happen, or bonding elastic modulus. So eventually, and then, so what kind of processing? We just use a specific processing, and then by adding some kind of nickel, chrome, and cobalt inside the ferrous material to enhance some kind of properties, and then energy potential well will be deeper. So that's why eventually we just arrive at the stabilized thermal expansion. How can we apply this one and then? So, we have some kind of luxurious watching. The watch, not electrical watch, is the ordinary one from the Swiss one, and very, very luxurious one. And then sometimes we can see some kind of machine component inside made of ferrous material. And then, but this one, the steel is rather affected by the heat. And then, how do you know? And then the railroad. And then during the winter and the summer, the length of the railroad will be changed significantly. That's why we just make some kind of break, some kind of periodic, some kind of repetition of this railroad, and then to make them let just go safely. And then, but the thing is that, and then for the circuit, tiny things and the needles should be the stable against the temperature gradient. You just buy some expensive watch from the Swiss, and then you have to pay around 10,000 USD. But the thing is that you just go to the desert area, and then time can be changed like relatively low. It's not good, right? So that's what, and then so we need to change the structure, and then how? By adding some kind of element inside. So final product, and then thermally stable, thermal stability, and then this is a better represent some kind of example. So once we know these some bonding characteristics, and they should be connected with the processing and property, and like this one. This is a very simple example. Not only this one, but also there are so many evidence example in there. So I can say, material science engineering, this is very fundamental, the majors, and also important, very crucial. Yeah, but unlike our expectation and mechanical guys, and then they just think about, and then outer shape and temperature and pressure is more important. Yeah, surely I agree. But to fabricate the higher qualities and the enhanced and also across the material limits and then constraint, and then in the moment we need to think about, yes, microstructures controlled by the processing to achieve certain requirements. So today I'm going to talk about what is the material science and engineering, and then why we just use a science and engineering both together. What is this kind of concept? What is the elements? How can I define these kind of categories? And then I just together with some I just provide some kind of useful example that also is part of our chapter 1 is about the bonding characteristics, and then so someone just write it down. So unlike my expectation, there are many people gave me a chatting. Actually, before starting this video clip, I'm pretty nervous, but you just give me many things, good stuff, good writings, and then so that's why I can make some more, how can I say that, I can give you some very smooth presentations about the material science. It's also my big honor. And then so next time this kind of case is just abrupt, and then next time, and then we just announce it in our board, and then I simply let you know, and we're going to have some kind of video clip and online broadcasting, and then I simply let you know at the moment. Then you have some kind of question, and then you can throw me in, and I will try to answer to the question. And after everything is stabilized, and then we want to make some kind of regulars the broadcasting, and also please welcome any kind of question, and that some kind of question is not associated with some material science. That's fine. I will try to make some kind of connection between each other, and then based upon my knowledge. And then today, so I hope that you really enjoy watching my videos in online. That's what, and then next time, and then so that's why I can say, and then see you.